In this video, we're going to prove something that'll be helpful when we show unique factorization in the fundamental theorem of arithmetic. And we'll use a sort of a iterative approach here as well. And then we're going to do an approach using strong induction. So we'll prove this twice. For the first proof, well, let's take the lemma first. Suppose we have P and then a collection of n of primes. Maybe they're equal. Maybe some of them are equal, maybe not. But we have some collection of primes. And we're going to have some k in n such that pk is equal to this. So what this is saying is P divides the product of q1 through qn. That's what this is saying. If P is dividing a product of primes, as in this equation shows, then P must be equal to one of the primes in the list. And that's what the lemma is saying. If P divides a product of primes, it's equal to one of the primes. So we're going to choose to write the P divides the product as Pk is Q1 times the product of the remaining primes. In particular, P divides the right-hand side because, well, it clearly is a factor of the right-hand side. And so since it divides a product, it divides one of the terms in the product. If P divides Q1 by our helpful theorem from before, P should be equal to Q1. If P divides the other portion of the product, then there's some K prime such that Pk prime is Q2 through Qn, and you just repeat this process. And you're going to repeat it until it terminates, and it'll terminate after at most n-1 steps. It could be at the next step P divides Q2, but you keep separating off the first term from the rest, and you keep doing this, and this will terminate after at most n-1 steps. And that's the end of the proof. Now, let's do this with strong induction. So the way in which we're going to phrase it with strong induction is we're going to induct on the number of primes that a prime is dividing. So if P is dividing just one prime, well, for P to divide one prime, it must be that K is 1 and P is Q1. So P is the Q1, the only one on the other side. We nailed it. Otherwise, with strong induction, or actually, I keep saying strong induction, sorry. For this one, it's just regular induction. Later, we're going to use strong induction. But nevertheless, suppose that the statement's true for n-1 primes on the right-hand side and any prime P on the left. Okay, so we're just going to suppose it's true up to Qn-1, and then we'll show it's true for n primes. Now, normally in class, we go from n to n+1. It doesn't matter. You could do that instead. You just need to show if it's true for one step, it's true for the next. So here in this proof, we're going n-1 to n instead of n to n+1. Same result. So we can again do the trick of the previous problem. So we associate Q2 through Qn, and we leave Q1 sort of outside the picture. So P is dividing this product, Q1 times the product of the remaining ones. So P must divide the first one, or it must divide the remaining ones. If P divides the first one, then P is equal to Q1, again, like in the previous video and in the previous proof of this. Otherwise, P divides the remaining guys. But if P divides the remaining ones, then there is some K prime such that Pk prime is Q2 through Qn. But now there's n-1 primes. So by the inductive hypothesis, P has to be equal to one of these. And that is the proof by induction for this case. And that's it.